All right. So let's begin. So just to sort of recap where we've been recently. We've been studying auctions for 4 classes now. And auctions are sort of a theoretically clean way to sell things and to solve other kinds of problems. And we've sort of talked about 2 kinds of objectives: maximizing social welfare, maximizing revenue. In fact, sort of lots of kinds of objectives, at least in single parameter domain. And as like a running example, at various times I've sort of speculated about how I might auction this slide dongle to you all. But I have a confession to make, which is that I did not buy this slide dongle at auction. I went into a store and it had a price, and I just purchased it at the posted price. And so, despite the fact that we've been spending quite a lot of time studying auctions, and auctions are run for high ticket items, and so you've heard of art auctions, and the FCC has run spectrum auctions, runway takeoff and landing slots are auctioned off, but like a whole lot of stuff in this country and around the world is not sold by auction. It's sold by attaching prices to them. And there's all sorts of good reasons for that, but maybe first among them are that auctions are just logistically difficult to arrange. To run an auction, I need to get, for example, all of the participants in the same place at the same time, and coordinating in what is basically an interaction. And although auctions have nice properties, they can exactly maximize social welfare, they can exactly maximize revenue. Just because of the logistical difficulty in running auctions, lots of things are sold with posted prices, which is very easy. I just decide on a price, I put it up in my shop window, and the first person who walks by is willing to pay the price gets it. And so what I want to study in this lecture is how we can take some of the things we've been sort of trying to optimize using auctions, welfare and revenue, and if not exactly obtain those benchmarks, at least approximate them. Okay, I mean, auctions are only a more powerful format than posted pricing. If I wanted to, I could describe a posted pricing as auction. I just have some price, in my mind. I solicit bids, and I just, give it to the lexicographically first bidder who bid above my posted price and charge them that price. So anything I can do with posted prices, I can do with an auction, and the reverse is not necessarily true. So we shouldn't expect to be able to exactly maximize welfare and exactly maximize revenue the way we have been able to with auctions, but the question is whether we can come close. Okay. And so, again, just as we've been talking about in our study of auctions, just as the mechanism design is extremely broad, and we would sort of zoom in on particular case studies to illustrate particular points. So knapsack auctions, when we're thinking about approximation and mechanism design, single item auctions, when we're thinking about revenue maximization. In this lecture, I'm going to think about posted prices for sort of our canonical example, which is single item auctions. I've got one item to sell and many bidders, but you can think of this as a case study. More generally, there's, for any mechanism design problem, you can think about how well you can approximate the optimal auction with something more like a posted price scheme. Okay, we're going to be thinking about pricing a single item, like a car, for example. How should I sell my single used car? And here's a model we'll think of. So let's imagine that there are K maybe recognizable types of buyers. Okay, it could be just one. of imagine that buyers are drawn from, their valuations are drawn from some distribution determined by their type. So if I don't know anything distinguishing the buyers, maybe they're all drawn from the same distribution, but I'll allow the flexibility that there might be k different types of buyers. Okay, like maybe when people knock on my door to inquire about my used car, the ones that are wearing top hats and monocles and kind of gold encrusted canes, like I make different inferences about their willingness to pay for the car than people who show up on my bicycles with flat tires. But these types of buyers can be based on whatever you want. Like demographic information you might have about them, purchase history, anything else. Like in an e-commerce setting, you might have quite a lot of information about buyers in general through cookie tracking or anything else. And the assumption is that buyers of type I will have their valuations drawn from some known distribution that might be particular to their type. The flexibility in allowing us to model different types of buyers is that I might imagine that buyers of one type are statistically different from buyers of another type, which I'll model by having their values drawn from a different distribution. Okay. Now what's going to happen, the thing about sort of posted prices is it's really a sequential setting, not right. Like if everyone was there at once, I can run an auction. The reason I'm using posted prices is not everyone is there at once. People are sort of walking by, they're entering my store, and at some point, someone might be willing to buy the item at the price that I set, at which point the item is sold. I can't sell it to the next person who walks in, even if they would have been willing to pay more. Okay, so a key part of this model is that buyers arrive one at a time until the item is sold. I have to make an irrevocable decision at some point whether to sell the item or not, and at that point, the item is gone. I can't sell it again. And what I'm gonna do is I'm gonna pick a price, and in particular, like if I wanted to, I could potentially pick different prices for bidders of different types. The assumption is when a bidder walks in, I observe their type. Okay, so I might have the price for the people in top hats and monocles and a different price for everybody else. Okay, but bidders of type I will face a fixed price PI, and the way we'll model their purchasing decision is sort of the natural thing. If their unknown valuation is bigger than the price that I offer them, then they're going to buy the item, and the revenue that I will get is the price. And if the price I offer them is bigger than their valuation, then they won't buy the item. I will get zero revenue, but I'll still have the item, which means that if a different bidder walks in tomorrow, I have the opportunity to sell it to them. And so, like the main question in this setup, okay, I know what the distribution looks like. Maybe I know how many bidders I expect to encounter in total. Are there ways for me to set these prices ahead of time? Okay, before I know who's actually going to walk in my door, such that when this plays out, the expected welfare or the expected revenue that I get is competitive, is comparable to what I would have gotten had I done the more difficult thing of trying to gather all of the bidders in one place and run an auction. Okay, does the question make sense? We're trying to do the same thing we did sort of in the auction setting, maximize welfare, maximize revenue, but in a more constrained setting. It's more constrained in that we have to just use fixed prices. In particular, it's more constrained in that we don't know who the bidders are going to be ahead of time. I have to make sort of, if I set a low price, I might sell it to the first person who walks in the door, and there might be people who walk in the door at a later point who would have been willing to pay more money, but the item was sold already. Okay, so does the problem setting make sense? Yeah.
Do you assume that like people come like or not also?
Yeah, let's say maybe that we have some sense for sort of what fraction of people are within each type. Okay, does the setting make sense? Okay. So, okay, this is the sort of mechanism design problem we want to solve. Let me pause for a short interlude to talk about sort of just like an abstract probabilistic problem that we'll see maps onto the economic problem we want to solve rather nicely. Okay, and okay, see how. So consider the following abstract game that is played in a series of n steps. Okay, so there's sort of time, which I'll index by I, and the way it works is that at time I offer you the opportunity to walk away with some monetary prize pi I, which is going to be drawn from some distribution gi. And the distributions are known in advance, but not the actual realization of the prize. Okay, so you know from the very beginning what distribution the prize for day I is going to be drawn from, but only if you make it to day I and I offer you the prize from day I, will you actually see the realization, the draw from that distribution of pi I. Now, at round I, after you see your potential prize for that day, pi I, you've got a choice. You can accept the prize, you can take it, walk away with it, enjoy it. But if you do that, you end the game. If you take the prize, you don't have the opportunity to see and take any of the future prizes. Okay, so in this interaction, you're going to take exactly one prize. And at each round, your choice is either to take the prize you've seen right now, or to reject it and continue. See what the prize is at day I+1. And so the question is, okay, the basic question in this setup is how well can you do? Like, what's the best strategy here, and how well can you optimize, the value of the prize you're going to take home in expectation? And a difficult benchmark is to compete with someone that I'll call a prophet who can see the future. Okay, like a prophet could see the future, could see not just the distribution on prizes every day, but actually the realized prizes every day. Okay, and what the prophet would do is he would just wait until he was at the day I, for which the realized prize was going to be the highest, and he'd walk away with that. Okay, so the expected profit of the prophet is just the expected value of the maximum over all of the n days of the realized prize on day I, right? Because the prophet's always going to perfectly select the maximum value prize. So that's the prophet he's going to obtain. Yeah. Yes, the distributions could be different every day, but you know what they are. The prizes are numbers, so it's like the number of buttons you win or whatever. And these are just distributions over those numbers. It could be different. Yeah. Because these are still distributions, right? So like this is the whole thing is a random experiment, right? Every time you play this, the realizations are going to be different. So every time the prophet interacts with this game, he will get payoff equal to the maximum of the realized payoffs. But what's his expected profit? Well, it's just the expectation of that card. That makes sense? Yeah.
Are we discounting at steps? Like, is there some kind of cost to waiting?
There's not. The profit is patient. Good questions. Other questions? Okay. So, like if you were a prophet, if you could see the future, you could always select the max prize, but you're not. And so the question is, how well can you do in this game? And so there's a reasonably immediate connection between strategies for this sequential game that I'll call threshold strategies and the pricing problem that we just defined. Okay, what is it? Well, let's say that in this sort of interaction in which you're competing with a profit, a threshold strategy is very simple. It's defined just by some real value threshold t, and it's the strategy that just waits until you see a prize that's bigger than t and accepts it. Okay, so you're just gonna, you've got some like quantity t you're holding out for, and you're just gonna like wait until you are offered a prize that's bigger than t, and if you are ever offered a prize that's bigger than t, you'll accept it. If you get to the end and you're never offered a prize that was bigger than t, you won't have accepted it. Okay, so that's a threshold strategy. And so there's an immediate connection between threshold strategies and pricing rules for maximizing social welfare. Okay, so let's think about that. So remember, I want you to identify the prize with the unknown value for the bidder and the threshold with the price. Okay, so remember how pricing works. I set some price for the good. A potential buyer walks into my store. If their value is bigger than the price, they buy it, and my revenue is the price that was paid. And the welfare is the value of the good that was purchased to the buyer who purchased it. Well, the threshold is the price, and the reward at that day is the value, right? Like, you know, in both cases, the interaction stops exactly when the reward or the value of the buyer is bigger than the threshold or the price. And the total reward obtained in the profit interaction is pi I. Correspondingly, the total welfare obtained in the pricing setting is VI. Okay. So there's this like one-to-one mapping between this interaction in which you're competing with a profit and trying to maximize your reward and the problem, at least if you solve it with the threshold strategy, and the problem of picking a price for a good such that you maximize welfare. Is that connection clear? So if we can solve this sort of stylized game in which you're trying to collect rewards competing with a profit, we will have solved the sort of more grounded problem of trying to figure out how to price goods so as to maximize welfare. Yeah. So you're saying like a threshold strategy can't be like exactly optimal in this interaction because if nothing else, like at the last round, if you haven't accepted any prize, you can accept that. That's true. So you might be able to do a little bit better than a threshold strategy by at least modifying it at the end to do that. But what I'm saying is any reward, any bound on the reward that we can obtain using a threshold strategy directly corresponds to a bound on the welfare we can obtain using an item price. Does that make sense? Yeah, so the thing we're going to do next is not derive like an exactly optimal policy in this sort of interaction in which you're competing with a profit, but is going to prove a bound on how well we can do with threshold strategy. Okay, so I just want to make sure this connection is clear, because what we're gonna do now is we're gonna sort of think about competing with a profit, but I want you to remember that, you know, really what we're doing is we're solving this pricing problem, at least if our objective is welfare. Okay. And so here's the theorem. So no matter what instance of this aim that we're given, right? So no matter what sequence of distributions are set out for us, there is a very simple policy, a threshold strategy. Right? Picks a threshold T and accepts the first prize that's above that threshold that is guaranteed to get expected reward at least half of that of the profit. Okay, right, remember, if you could see the future, if you were a prophet, you would always select what turned out to be ex post the maximum prize. You can't do that because you can't see the future. Okay, so achieving exactly this benchmark would definitely be impossible. The statement is there's an extremely simple strategy, a threshold strategy that gets half of that benchmark. Okay, that makes sense. Okay. So let's prove it. So first I want to introduce some simple notation just to make the derivation a little bit cleaner. So if I've got a real number z, I will write z plus to refer to the positive part of that number, by which I just mean the maximum of z and 0. Okay, so like z plus is just equal to z if z is already a positive number, but if z is a negative number, then z plus is just 0. Okay. If you're like a machine learning person, you might call this a ReLU activation, but you shouldn't. Okay. Now, I also want like a simpler notation for the benchmark we're competing with, the maximum realized reward over the n time steps. And I'll just call that V star. Okay, so our goal is to give a threshold strategy that gives us reward that is at least half of V star. Okay. Now, note that although we don't know what the realizations of the rewards are going to be, we do know how they're distributed because these distributions G1 through Gn are given. And so we can compute what is the expected value of V star, for example, right? Like we could, in principle, like run simulations in our head of how well the prophet would be able to do. We can sample from these distributions and compute the maximum realization of the samples. And so we can figure out distributional properties of V star, in particular its expectation. And the threshold strategy that I want to analyze is just going to set the threshold at half of the expected value of V star. Okay, so I know, on average, how well the prophet is going to do, how much profits the prophet will make. And my threshold is going to be half of that. I'm going to accept the first reward that's offered to me, whose value is at least half of the expected profit of the prophet. Okay, does the strategy make sense? This is the strategy we're going to analyze, and it's well defined. It's defined in terms of quantities that we know. Okay, and just to sort of make the connection to this pricing problem, which is the thing we really care about, clear, in the proof, I'm going to use the language of the economic application that we care about, the pricing problem. Okay, so instead of saying we accept a prize, I'm going to say the item is sold. Okay, right? If we accept the prize, if the prize is above the threshold, well, that's like saying we sell the good if the value of the buyer is above the price. And if we don't accept any prize, I'll say the item is unsold. Okay. Just to make the connection to the pricing problem. And so we're going to prove this theorem, which is called the profit inequality, by decomposing the expected reward into two quantities that we can also relate to the application we have the pricing from. Okay. I want to separately think about the expected revenue that we make by pricing in this way, and the expected utility that the buyer gets. Okay. So that's going to be the plan. So the thing that we want to show is that the expected welfare or reward is large, but we are likely to sell the good to somebody who has high value for it. We're likely to accept a large reward. And so, since our plan is to sort of relate welfare to revenue and utility, and separately bound those two things, I want to think about if, in the end, I end up selling the good to some buyer I at price P, which just means selecting the ith reward, what revenue and what utility for the buyer results. Okay, so pretty immediately, if I sell the good to some buyer I at price P, then my revenue is P. Okay, I get P dollars, that's what I sold it for. And the utility of the buyer is VI minus P. Because their value for the good was VI, but they had to pay P dollars for it. Okay, so their utility was VI minus P. And so welfare, this thing that we want to argue is large, it's just the sum of the buyer's utility, it's just the sum of the buyer's utility and the seller's revenue. And so our strategy is going to separately show lower bounds on revenue and buyer utility. Okay, if we can show that both of these things have to be large, or if at least one of them has to be large, then their sum, this thing that we care about, has to be large. That's the overall strategy here. Okay, makes sense. Okay. So let's think about these two things separately. So first, what is our expected revenue? Well, that's pretty simple. If we sell the item, then we get revenue P equal to the price we set. And if we don't sell the item, then we get revenue 0. And so our expected revenue is just P, the price we set, times the probability that the item is sold. And we know what price we're setting in the strategy we're analyzing. I told you that already. The price is just half of the expected value of the benchmark, half of the expectation of V star. And so our expected revenue is just half of the expectation of V star times the probability that the item is sold at that price. Okay. We don't really know what the probability that the item is sold is, but this is at least a correct expression for what our expected revenue is going to be. There. Okay. Let's think about buyer utility, expected buyer utility. This one's expected revenue is easy. There was only one of us who made P dollars if we sold the item. Buyer utility is a little more complicated. There's N buyers, and what their expected utility is going to depend on who the item ends up selling to. So let's think about things this way. There's sort of two cases for how bidder I might contribute to the expected buyer utility. So it might be that by the time buyer I walks past our store, the item has already been sold, in which case buyer I doesn't even have the opportunity to consider buying it, and definitely will not contribute to social welfare, will not get any utility out of it. Or It might be that when buyer I wanders past our store, we haven't sold the item yet. In which case buyer I gets to consider whether she wants to buy it. Right, if she has the opportunity to buy the good, her utility will be the positive part of VI, her value for the good, minus the price. Right, because if the price is less than her value, so VI minus P is positive, then she will buy the item and her utility will be VI minus P. And if her value for the item is less than the price, if VI minus P is negative, she won't experience negative utility, she just won't buy the item and she'll have utility 0. Right, so buyer I's utility will be the positive part of her value minus the price if by the time she gets to the item, it hasn't yet been sold. Right? And so what's expected buyer utility? Well, we've got to consider the contribution to this quantity of all n of the buyers. So it's the sum over all of the buyers of their expected utility, assuming that the item is available by the time we get to them. So the expected value of the positive part of VI minus the price. Okay, but this is just their expected utility conditional on the item being available for them to buy. So we have to multiply by the probability that the item hasn't yet sold by the time that we get to buyer I. Okay. Under the event that the item is available when we get to buyer I, this is their expected utility. And so our expected overall utility by linearity of expectation is just the sum of these terms over all of the buyers. Makes sense? Okay. It might be hard to understand the quantity, the probability that the item has not yet been sold at time step I, right? Because that's a complicated expression. There's a lot of ways in which the item might not have yet sold at time step I. But we know that the probability that the item hasn't yet sold by time step I is at least the probability that the item never sells. Right? Like we can upper bound this by the probability that the item is unsold at the end of this whole interaction. Okay. So whatever this quantity is, which is a little hard to think about, it can only be bigger than the sum over all of the buyers of the positive part of their value for the good minus the price times the probability that the item never sells, doesn't sell even to the nth buyer. Because in particular, if the item never sells, it was available to each of the buyers at the time that they arrived. Okay, does that make sense? And this is the expectation of the sum of a bunch of quantities. Now, the sum of a bunch of non-negative quantities, because this is the positive part of value minus price, right? So this quantity can never be negative, quantity inside the expectation. And so if I've got the sum of a bunch of non-negative quantities, it can only be larger than the maximum of those quantities, because the sum includes the maximum, whatever it is, and we don't have any like cancellations, some of the terms are negative. So we can further upper bound this by the expected value of the maximum over all of the buyers of the positive part of their value minus price. Again, multiplied by the probability that we never sell the item. Okay, that makes sense. Okay, and like just making our bound even a little bit worse. Let's just get rid of this positive part now. Okay, like all this positive part is doing is making our quantity larger, because it might be that sometimes this term is negative, and when it's negative, we're sort of raising it up to 0, and otherwise we're leaving it unchanged. Okay, so if we get rid of the positive part, then we only make this quantity even smaller. Okay, and well, P is just a constant. So what we're left with is the product of the difference between the expectation of the maximum value. Okay, this is like the maximum social welfare, the benchmark that would be obtained by the process, minus the price, times the probability that the item never sells. Okay, each of these steps, we've only made the quantity smaller, and so whatever the expected buyer utility is at least this thing we ended up with at the end. Okay, and just sort of remembering what these quantities are. The maximum buyer valuation. This is the profit benchmark. This is the thing we call V star. And the price that we set in the threshold strategy we're analyzing was just half of the expectation of V star. Okay. So this difference here, the expected value of the maximum bid, V star minus the price, minus half of V star, is just half of V star. Right? It's V star minus half of V star, which is half of V star. And so this whole expression, whole bound we've computed, is just half of the expected profit of the profit times the probability that we never sell the item at that point. Okay, clear? Okay. So remember, our goal is to bound the expected welfare of the allocation that we end up with when we use this pricing rule. And we noticed at the beginning that welfare is always the sum of the revenue of the seller and the utility of the buyer. And so expected welfare is just the sum of the expected revenue of the seller and the expected utility of the buyer. And we separately bounded each of these two things with quantities that we didn't really, it was hard to put a number on, right? Like we bounded expected revenue with half of the benchmark times the probability that the item was not sold. Okay, but like we don't really know that we don't really know the probability that the item is sold. We bounded expected utility with half of the benchmark times the probability that the item is unsold. Okay, we don't really know the probability that the item is unsold. But we do know that the item is either going to be sold or not. There's only two possibilities. And so when we write down our bounds for the expected revenue plus the expected buyer utility, well, we get half of the profit benchmark times the probability that the item is sold, plus half of the profit benchmark times the probability that the item goes unsold. Or in other words, half of the profit benchmark times the sum of the probability that the item is sold and that the item is unsold. And although we don't know anything about what either of these two quantities is, we know that their sum has to be 1, because there's only two possibilities here. Either the item will be sold or the item will be unsold. So this sum is 1. And our expected utility is going to be equal to half of the optimal benchmark. Okay. Does that make sense? Yeah.
This is trying to prove that it's going to be. How can you do that by
So I don't follow. So there's two. Like maybe you can. Maybe that there's a. Let me guess what the source of confusion is. You can tell me this quantity, half of the expected profit benchmark, comes in two places. On the one hand, it's like in the theorem statement, it says like, this is the welfare we're going to obtain. On the other hand, it's also in the pricing strategy. The price we set is equal to half of the expected benchmark, which is a quantity that we know, so we can use that for pricing. So maybe I don't understand the question, but the pricing rule we use is very simple and uses information that we have available to us. So it's just the distribution. Figure out what the expected profit benchmark is going to be, take half of that and use that as our fixed price. And what we've proven is that if we do that, if we follow this simple pricing strategy that uses only information that's available to us, then in expectation over the randomness of the buyer evaluations, the welfare we will obtain is half of the benchmark of half of the optimal welfare benchmark. Does that make sense? Good question. Other questions? Okay. So having solved, having proven this profits inequality, P-R-O-P-H-E-T, we have sort of an immediate implication, confusingly not for profit, P-R-O-F-I-T, but for welfare maximization. It means that using a single fixed price, actually independently of the types of the buyers. Remember our strategy space here when we defined the pricing problem, right? We sort of said, well, like different buyers might be drawn to different distributions, and like we have the power if we want to set different prices for people who show up in top hats, for people who show up on bicycles. But the strategy we just analyzed actually doesn't do that. It sets just a fixed price that it uses for everybody, so you can just, like throw it onto the side of your car. The price is just half of the welfare benchmark, the expected welfare benchmark, and we show that this simple rule, despite the fact that it doesn't require synchronously gathering all potential buyers in one place and running an auction, nevertheless can get half of the expected welfare of the VCG bank. Okay, so it's doing this, not only in sort of an easier to implement way, since you don't need to like gather everyone in one place, it's also doing this sort of despite what you might have thought was sort of like a crippling information theoretic disadvantage, which is that it has to make decisions about whether to sell an item or not with uncertainty about what the bidder realizations are going to be, like not knowing who's going to like walk in the door tomorrow, or not even knowing the valuations of people who've already walked in the doors. They don't have to report them to the mechanism. They're just making purchase or no purchase decisions. In contrast to the VCG mechanism, which gets to use all of that information, gets to see the valuations of all of the buyers, all of the potential buyers at once. Okay, so the pricing rule doesn't use any of that information. It has to make decisions before some of the buyers arrive, and it doesn't even get to ask the buyers who did arrive what their valuations were, and still it does at least half as well as the VCG. Okay, so that was for welfare. What do we know about revenue? I suppose the reason we're selling our used car is not to make the world a better place and maximize welfare, but rather because we want money. So remember that a single item auction is a single parameter domain. And we had this characterization that we proved last class when we were studying revenue optimal auctions. That sort of said, well, for any monotone allocation rule, when we pair it with the unique pricing that makes it dominant strategy truthful, the expected revenue that we get from that allocation rule is just, it sort of looks like a welfare maximization problem. Except instead of wanting to give the item to the person who has the highest value for the good, we want to give the item to the person who has the highest virtual value for the good. So the virtual value for the good is related both to the buyer's realized value, but also somehow from the distribution from which he was drawn. And the virtual values could be positive or negative, which means that the revenue maximizing auction, at least, will sometimes not allocate the item, right? Like the way you maximize the virtual value of the person that the item is assigned to is by assigning the item to the person who has the highest value, the highest virtual value, which is the same as the person who has the highest value, if that virtual value is positive, and otherwise not assigning it to anybody. Right, so that, like in some sense, intuitively, the way revenue maximizing auctions make more money than welfare maximizing auctions is by artificially restricting supply, by sometimes not selling the item. But because we were able to cast revenue maximization as a virtual welfare maximization problem, we can use the machinery that we just developed to maximize welfare with pricings, to maximize revenue with pricings as well. Okay. Just that, you know, instead of mapping values onto the prizes that are available to our profits, we have to map virtual values onto those prizes. So the optimal revenue, given the optimal revenue, which we'll call opt, this is sort of the benchmark that we would achieve if we got to run the profit maximizing auction in the last class, is just the expected value of the maximum of the positive part of the virtual valuation. Because if the largest virtual valuation was positive, then we give the item to that person, and if it was negative, we don't give the item to anybody. And so this expression is equal to our expected revenue under the optimal allocation rule that gives the item to the person with highest value exactly when their virtual value is negative. And so we can map this revenue maximization problem directly onto our reward selection problem and compete with the profit there. Okay, so now rather than sort of viewing the reward that's realized at day I as the value for bidder I, as we did when we were interested in welfare, we'll view the reward that's realized at day I as the positive part of the virtual value of bidder I. Okay, so the expected profits of the profit, this benchmark that we now know how to compete with, well, what's the profit going to do? He's going to take exactly the largest reward, which is equal to the virtual value if the largest virtual value is positive and is otherwise equal to 0. Okay, so the benchmark of our profit is now the optimal revenue benchmark obtained by the revenue maximizing auction. And so by applying exactly the same threshold strategy that we just derived, we know that we can obtain virtual value, at least half of opt, by setting the threshold strategy, by setting the threshold to be opt over 2. And what this corresponds to, right, like this is a threshold on virtual values. So to map this back into a pricing rule, remember, buyers are not computing their virtual values. What they're doing is they're just buying the item when their actual values are bigger than the price. right? So to implement a strategy that sets a fixed threshold on the virtual values through pricings, which correspond to thresholds on the actual values. What we need to do is we need to map a number t, this threshold in virtual value space, back to value space by applying the inverse of the virtual value. Okay, so if the buyers are going to buy an item at price pi exactly when their value bi is greater than pi, what we'd like them to do is buy the item exactly when their virtual value is greater than 1/2 times opt. And so the price that we should offer to buyer I is the inverse of their virtual value function applied to opt over 2. Does that make sense? When a buyer, when a buyer faces this price, they will buy the good when their value for the good is greater than this price, which, just by applying the virtual value function for that buyer to both sides of the equation, corresponds to exactly when their virtual value is bigger than our threshold, opt over 2. And so this immediately gives us a pricing rule that gets us now within a factor of 2, not of welfare, but of revenue. The factor of 2 of the revenue of the optimal auction. But note now that when we're maximizing revenue, the actual pricing rule looks a little bit different. So remember, when we were maximizing welfare, even though the buyers came from potentially different value distributions, had different types that we could recognize. There were the wealthy eccentric buyers, the scrappy buyers looking to get their first car. When we're maximizing welfare, we offered every single one of them the same price. But that's not what's happening anymore when we're maximizing revenue. Even though we have a uniform threshold on their virtual values, this transformation, since buyers who are drawn from different distributions, buyers who are of different types, will have different virtual value functions, this transformation will correspond to offering them different prices. So we're going to offer a higher price to the guy who shows up in a top hat at our door, the guy who shows up with a broken bicycle. Okay, which makes a lot of sense for revenue. That's it. Well, stick around in case there's questions. And otherwise, I'll see you guys next week.